I have you loud and clear.
Hello.
Hello.
Hello. Welcome. Science.
And that is to say,
Physics, medicine, nature,
or
Space. Time.
the brain,
Life. The universe.
Hello! This week we're leaving planet Earth in the search of a new home. Is there a planet B? How could we get there? And I take a spin at astronaut training.
And you can talk to us?
Yeah, it's okay. I was expecting it to be quite intense, but it's actually just like a massive roller coaster ride.
I'm Izzy Clark, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Last year, one very prominent Cambridge scientist made a rather shocking prediction.
I strongly believe we should start seeking alternative planets for possible habitation. We are running out of space on Earth, and we need to break through the technological limitations, preventing us living elsewhere in the universe.
Professor Stephen Hawking stated that to secure the future of us humans, we need to colonise another planet. But would you want to go?
3, 2, 1, 0.
No. No, I definitely not. No.
Yeah, it would be an adventure and something new, exciting.
I might go for a holiday. Probably not to live there, though.
I don't know, you'd have to have some entertainment because it'd be a bit lonely, wouldn't it?
Why would we need to leave planet Earth? Existential risk is the risk to the existence of something. And in this case, that something is us. As Adrian Curry from Cambridge University explains.
So one set of them are things that are done to us. So take, for instance, a large asteroid hitting the Earth, or a supervolcano erupting, or a major solar flare, basically a big gust of radiation coming out from the sun. There are also dangers that we do to ourselves. Climate change. One of the things we know that's going to happen with climate change is an increase in the global water levels. What's that going to do? Well, it's going to mean a lot of people are moving, right? So the upshot of this is there's going to be a large number of climate refugees. What's an upshot of a large number of climate refugees? Well, we can sort of tell from history that often this creates pressure on certain types of political systems, and so the political environment becomes a lot more problematic. At the same time, with large amounts of movement of people, that increases the chances of epidemics, right? So you might have a lot more disease going on. In addition to that, with climate change, there's going to be many more, as it were, smaller disasters, more droughts, more tsunamis. At the same time, of course, you've got various types of biodiversity collapse, which is linked to climate change. And we really don't know to what extent living systems are dependent upon certain levels of biodiversity being maintained. When you start thinking about all of these things happening at the same time, you then sort of see a sort of perfect storm. Would that lead to human extinction? I'm not sure, but it's at least reasonable to think that it's going to put a lot of pressure on our species, and it's certainly going to put a lot of pressure on our civilizations.
So pretty ideal to have a backup plan should something like that happen.
Yeah, and I take it that that's one of the sorts of motivations for wanting to, colonize other planets. But I think we should care about a lot more than just human survival, right? We also care about our lives being good. And moreover, we care about the whole population. The idea that we might let the vast majority of the human population die so we can then have a few survivors on some other planet seems in itself deeply problematic.
How can you even model something like this? Because obviously these are quite low probability of happening, but have a very high risk.
It's incredibly difficult. Some of it involves just using what we do know about, for instance, planetary systems. We can model things like what happens when great big rocks hit the Earth. We can model things like what happens when different economic systems sort of run into each other. And that can start giving you some kind of hint into how these things work. But I think the real question, in a sense, is not how do we know about these things, but rather how do we manage the fact that we don't know about these things.
With this, say if we did have something like climate change going crazy, or maybe even something like a really strong solar flare, is there a way that we could defend ourselves?
Potentially, we have this new technological power. With the case of solar flares, right? We know that if an extreme solar flare happened, that would knock out all of our space technology. And so what you want is some kind of backup system. Maybe, I don't know, a bunch of satellites on standby on Earth that you can just shoot up if this were to happen. So one of the advantages of these new technologies is that they enable us to defend ourselves against these old existential risks, right? Things like great big rocks. But they also present these new existential risks that come from emerging technologies.
What do you think some of the threats might be if we did colonise another planet? Is that something that we have to think about as well?
One scenario that comes up a fair bit in science fiction is the idea that if we were colonizing other planets, there might be other life there. And other life might have new types of parasitism. There might be particular diseases that we're not equipped to handle. So you have a sort of a space analogy between what happened when Europeans colonized the Americas and brought this new bunch of diseases that the indigenous people just hadn't had time to get immunities to. Maybe there are things like that. But there are other ways of thinking about this as well. So one reason why we might worry about colonizing other planets is we're going to create isolated, divergent groups of humans, and they're going to be highly technologically advanced, but isolated. And there's a chance that that could lead to wars between these groups, and that seems very, very bad.
That's certainly one way of putting it. Adrian Curry there from the Centre for the Study of Existential Risk. So there's lots of reasons to stay and there's lots to go, but the big question is, can we? I'll be looking into some of the problems we'll have to solve, but probably the biggest is finding a suitable planet, because Earth has a lot going for it, especially when it comes to atmosphere. Are there any planets with atmospheres like ours? I took a trip to Cambridge University's Institute of Astronomy to speak with Niku Madhusudhan.
The Earth has a unique combination of chemicals on its surface and in its atmosphere, which makes it very conducive for life. So here's a planet which is at the right temperature with an atmosphere which can sustain liquid water on its surface, and we know that life can thrive in such an environment.
Now, you look into atmospheres of exoplanets, planets outside of our solar system. So when you're looking for these, what exactly are you looking for?
Ultimately, right, the holy grail of the field is to find a planet, let's say, exactly like the Earth in all manner of things. It's one thing about finding a planet at just the right distance from the stars, so it could have the right temperature to have liquid water on its surface. But it's quite another major effort to be able to find what's the composition of its atmosphere. So when we look at Earth-like planets around other stars, probably we'll start with looking for the same signatures that we have in our own Earth. Signatures of oxygen, ozone, and other chemicals like methane and so on.
Have you had any luck with this? Like, how common or uncommon are these biomarkers?
So far, we do not have any atmospheric signature of an Earth-sized planet.
Still looking.
So we're still looking. But what we do have, lots of giant planets, like Jupiter-sized planets, for which we have found several chemicals in their atmosphere. So that's a place where we are at right now with our current facilities. And that's actually looking quite promising. We have discovered molecules such as water vapor. We have discovered carbon monoxide in several planets. We have discovered exotic chemicals like titanium oxide, for example. These giant planets open a wide range of scientific questions on their own, even before we get to smaller Earth-sized cooler planets. So when we go to smaller planets, that's the challenge, is that we don't know what their atmospheric composition will be.
So how can you go about looking for these smaller planets?
So if you want to detect the atmospheric composition, atmosphere of a Earth-like planet around a Sun-like star, that's extremely hard.
So that's looking at a situation like us, a nice tiny little planet like us, next to a sun that is pretty big.
Exactly.
In comparison.
100 times bigger. And that is very hard to measure. So why not look at stars that are much smaller than the sun? There are these classes of stars that are about a tenth of the solar size. And that becomes much more feasible. There is another advantage of this, is that because these small stars are also cooler. If the star is cooler, you can be closer to the star and still maintain Earth-like temperatures. So now we are talking about a scenario where you could have habitable planets which are similar temperatures as Earth, but much closer to the star. So you can observe them much more frequently. So that's where we see some hope. So maybe within the next 4 or 5 years, we actually might be able to find atmospheric signatures of Earth-like planets around small stars.
And what is the process that you use to say, oh, look at that star over there. There is a bit of hydrogen there. There is some nitrogen over there.
The most common type of observation we make is called transit spectroscopy. You are looking at a star constantly. So if nothing passes in front of the star, you see the light from the star is constant. When the planet comes in front of the star, you see this light dipping by a little bit as long as the planet is passing in front of the star. What you'll see is that the atmosphere absorbs in some wavelengths and not in others. And then we use detailed numerical methods to try to extract the chemical information that's in that spectrum.
Niku Medasuthan. Now, one candidate system has been found, TRAPPIST-1, at a mere 40 light years away. That's roughly 235 trillion miles. It's a system with a small star, like Niku looks for, with 7 Earth-like planets orbiting around it, each with masses and radii similar to those of our own.
They have a density which is not that different from the planets of the solar system.
That's Amaury Trio from Birmingham University. He's discovered over 100 planets outside our solar system.
For instance, TRAPPIST-1e, one of the planets of that system, has a density which is very, very similar to that of the Earth. As far as surface conditions or whether they have an atmosphere, we still do not know. With telescopes like the extremely large telescope in Chile or the James Webb Space Telescope that NASA and ESA are about to launch in 2 years' time, we will have a chance to find out whether the planets have an atmosphere, what the climate is, what's the chemistry of the atmosphere, how much greenhouse gas they have, and therefore deduce the conditions on the surface, how hot it is, and whether liquid water could exist. However, this at the moment remains still unknown, and we're really very much looking forward to the day that we can say something about this.
Why are we always focusing on this sign of water?
Liquid water provides a really good substrate for molecules to move about, for life to use. You need something neutral in which your molecules are going to combine with others in order to produce something more interesting. And water is one of the most abundant molecules in the universe and is one that is actually really practical to make chemistry. It would be strange if a majority of biology in the universe didn't use it.
Now, you said you're comparing the density, so why is that important?
Density is important because it's telling you something about the composition of the planet. Here, when we look at the planets, we see that the density is similar to many of the planets of the solar system, so it indicates a lot of rocks. But interestingly, some of the planets of TRAPPIST-1, like TRAPPIST-1b, for instance, the closest to the star, has a density which is lower than what you expect for rocks, an iron core like the Earth has. And it implies that there is something lighter on the planet, either a very thick atmosphere or maybe a big layer of water or ice. We don't really know, but it's really intriguing.
That would be great news if it might be some sort of ice or water, surely.
Well, although you want water, you don't want too much water either. Here, our numbers would be consistent with the planet having 250 times more water than the Earth has.
Ooh.
So it means no land, it means incredible pressures at the bottom of the ocean, and so it might not be that great. I think you want some water, but not so much water.
Now, we talk about our system here on Earth and the system that we're in being quite unique, but we've got this TRAPPIST-1 which looks quite similar. I mean, are these quite uncommon systems? Are there other candidates like this?
It's a very good question. TRAPPIST-1 is similar to the solar system in the properties of the planets, but is very different in other properties. For instance, the planets are really close to the star. The star is small, it's cold, and so in order to have the right temperature, the planets are really hugging the star, and the entire system fits within 6% of the distance between the Earth and the Sun. So it's a tiny, tiny planetary system compared to the solar system. In terms of uniqueness, we feel that the solar system around stars like the Sun exists about 10% of stars like the Sun. We don't really know yet. For systems like TRAPPIST-1, we also are quite uncertain how frequent they're found, but our early numbers are rough, but they indicate 30, maybe up to 50% of stars that are this small, 10% of the size of the Sun, could have planets that are terrestrial, and a large fraction of those would have planets that are temperate as well as being terrestrial, meaning that they're very interesting for us to study.
And when we say temperate, we mean having those conditions where water could potentially exist.
Often people in the past have used the word habitable as to say the planet is within the habitable zone. But I think this word is fraught with misconceptions and preconceived idea. We see habitable as, okay, if I land there, it'll be okay for me.
Because that's what I'm thinking. I'm like, okay, it's habitable. Great, let's
go. Yeah, let's have a drink on the beach. So the word temperate, I think, has less of that baggage. And that's why I think we prefer using that now, at least within our team. And temperate means that the planet has the potential to be habitable.
Okay. Is there any way that we might be able to go there?
Going there is, I think, so far the stuff of science fiction. It's incredibly far away. I don't think we quite realize how far distances or how long, how big distances are in space. It's 10 times further than the nearest star is to us. And at the current speed of spacecraft, the fastest of them, one of the Voyager probes, is going to take about, I think, 50,000 years to reach that distance. It's a quarter of the lifetime of our species on Earth. It's really long.
Anne-Marie Trio from Birmingham University.
So what we were trying to do with this paper is to demonstrate the ability to type using brain signals, anywhere between approximately 4 and approximately 8 words per minute, a factor of between 2 and 4 faster than what's been demonstrated before.
Each month, the eLife podcast talks to some of the world's best scientists. Join me, Chris Smith, as I hear about breathtaking discoveries hot off the press. Find the eLife podcast on iTunes or listen and download for free from nakedscientist.com/elife.
Still to come on The Naked Scientists, I take a trip to an astronaut training facility and explore the hazards of life in space. But first, we've just heard that certain Earth-like systems are simply too far for us to reach. So, to search for an alternative home, astronomers need to look closer to our blue dot. Specifically, Mars. Andrew Coates is from UCL's Mullard Space Science Laboratory and principal investigator for a panoramic camera that will be visiting the red planet as part of a new rover mission called ExoMars 2020.
Mars is one of the places where life could have started 3.8 billion years ago, around about the same time that it was starting on Earth, because conditions then were very much like the Earth, much thicker atmosphere, a magnetic field and volcanism going on. And it's one of several locations in the solar system where there could be potentially life.
How are we actually exploring the planet?
Well, what we're doing at the moment is using a combination of orbiters and rovers. Currently, NASA has the Curiosity mission on the surface looking for signs of water and habitability. And what we want to do in the future is actually to extend that search now and look for signs of life. And so we have the European Space Agency and Russian mission called ExoMars. That's going to the surface of Mars. And what we'll be able to do with that is actually drill underneath the surface of Mars for the first time up to 2 meters. The surface of Mars is a very inhospitable place at the moment because it's got a very thin atmosphere, which means you have a high radiation environment, a high ultraviolet environment. It's also a very oxidizing environment and thin carbon dioxide atmosphere, so it's not conducive for life now. But underneath the surface, that's where we hope the evidence for life having been on Mars, that's where it'll be.
So how do you know where to drill? Because obviously we're down here on Earth. How can you control that?
One way to do that is with the instruments which look at context. So our one is the main context instrument, really, the PanCam, panoramic camera system. Inside the box, basically, we have 3 cameras. So the 2 of them are wide-angle cameras, and these are spaced 50 centimeters apart. So with that, we get stereo reconstruction, and better than the human eyes can do. Each of those cameras actually has a little filter wheel on the front of it. So this has 11 filters for each of the 2 cameras. So with that, we split up the light into its constituent colours and measure basically the reflectance spectrum of rocks. We're trying to identify the rocks, and in particular water-rich minerals, to see where the right place is to drill for signs of life.
How will this all work together? Because it's got quite a lot of different instruments on this rover.
Yeah, so with the context instruments, of which PanCam is one, and then we get the other context as well, we actually get a sample from underneath the surface. So it drills underneath the surface, and so we get the sample from there, bring it up and put it on the same rover into the analytical drawer. And so there are more instruments inside the analytical drawer to actually look for signs of life on Mars.
Obviously, all of this, no humans. How far away is that?
The problems with sending humans are the expense of doing it, $20,000 a kilogram to launch anything into space at the moment. So by the time you've sent a person, the water, the food, it's a lot of kilograms and a lot of money to actually do that.
Because Elon Musk has said that it can be possible. He's got this blueprints to colonise Mars. So can you tell me a bit more about that? What does that involve?
Yeah, so he's building a very large rocket system. I mean, currently they have the Falcon 9, which can re-land the launcher actually back on Earth, and that helps to save cost. But what he's doing now is building something called a BFR, which stands for Big Something Rocket, and we think the something is Falcon.
Not something else.
Yeah, not something else. But it really is big, and that potentially could be taking 100 people to Mars.
Oh, wow. So how long is he planning to do that, and can they stay there? What are some of the problems with it?
Well, he says that they want to launch the first 2 missions in 2022, and then in 2024 maybe take a couple of people to Mars. I think that is wildly optimistic because, of course, they've got to develop the technology to be able to do that. They want to try and use the surface of Mars, using water from the under the ground, carbon dioxide from the atmosphere, to make methane and oxygen. And so with that, you could build the fuel to come back. Now, this is the realms of science fiction, really. There's a lot of things to do. First of all, landing in this very thin atmosphere. The other big challenge with Mars is Mars doesn't have a global magnetic field, so unlike the Earth, which has a magnetic field which helps to shield us and our atmosphere from radiation from space, that is dangerous to humans. And so actually having that on the surface and being able to deal with it, even taking people there at all, that's something which has to be really thought about.
Are there any plans on, if we were to stay on Mars, how we might live there, what life would be like? Would we even be able to have houses? How could you build anything like that?
We wouldn't be able to do that very easily because there are a number of differences. I mean, the atmospheric pressure is low. It's carbon dioxide atmosphere, so obviously you've got to have an atmosphere including oxygen. So that would be done inside, probably huts or whatever, or things actually built on the surface. So you'd need that type of arrangement. You need to keep the inhabitants warm. You need to, of course, grow food and things like that. So, I mean, people talking about colonisation, Elon Musk, of course, is one of the people who has wonderful plans for that. But, the technical challenges of doing it, the difficulties are certainly quite significant at the moment. We don't have the technology to do that.
And how optimistic are you? Do you think it could be done?
I think potentially it could be done if the political will and the money and so on was there. One could get over the technical challenges. It's always great to aim high and have the possibility of solving the technical problems to do it. But, we'll take a little while to actually do that.
So we'll keep working on that. Andrew Coates there. But what will our rockets of the future look like?
Very, very, very large. Probably fit like tens of thousands of people on there.
I don't think they'll exist. I think it'll be a Star Trek one. Beam me up, Scotty.
Super sleek. I don't know what else. You literally don't have to do anything. Like someone's got those full of robots.
I don't know. I think they're probably sort of quite small, to be honest, because they're probably go out mining first.
Well, what do the experts think?
I'm a bit of an optimist, and I would like to think that the human race will do very well in terms of space travel.
That's James Sadler from Airbus Defence and Space UK, who designs propulsion systems.
There's these devices called O'Neill cylinders, which are basically very large space stations which spin in space, so they have the appearance of having gravity. But of course you can have more of them based around Mars, Venus, Earth. They would be able to act as refueling stations, stop-offs if you're going for a deep space journey, or even you could imagine it a bit like a cruise ship where you go from port to port and the space stations become the ports.
That may sound like something from Guardians of the Galaxy, but NASA has looked into these spaceports, and whilst it's theoretically possible, it's just too expensive. Current spacecraft use chemical components, a fuel and an oxidizer, which essentially start a massive fire and the rocket blasts off like a firework.
The better the propulsion system you have, the faster you can get somewhere or the further you can go. At the moment, if we wanted to go and take the human race somewhere else, we would be limited probably to Mars at a stretch. If we were looking to go even further into space and we wanted to go out to another star system, for instance, so say, for instance, we found another habitable planet nearby, the technologies to do that for a human ship do not currently exist. But if we wanted to go and have a look, we would be able, for instance, to send very, very small spacecraft, say the size of a postage stamp, using some very novel techniques where we use a solar sail. So we have this very light material which stretches for a long way away from this very small spacecraft, and we can use lasers or the sunlight to push very gently against it for a very long period of time. So it's a bit like sailing on the sea in a gentle breeze. You're not going to go anywhere very fast, but over a period of time you can get faster and faster, and it might give you enough push to get away.
But not exactly ideal for us humans.
We're now looking at the next generation, which is the electric propulsion. The way it works is you take an inert gas, in our case we usually use xenon, and you knock some of the electrons off it to give it a charge. Once it's got a charge, you can use electric fields to give it some speed. And in this case, you would be able to take an ion and take it up to about 35 kilometers per second in terms of the speed it would come out of the back of the rocket.
And does that then give it a bit of a push, and that's what allows us to keep moving?
Exactly. So what you have is a combination of mass and speed, which gives you a momentum. Every time you take a piece of mass and you chuck it out the back of the rocket at a speed, you acquire that momentum yourself. The faster you can throw a mass out the back, the more momentum you get, or the higher the mass you throw out at a lower speed, the more momentum you get. In electric rockets, the idea is that you throw very small masses very fast, whereas in conventional chemical rockets, we throw a lot of mass a lot more slowly. And that's where the efficiency of electric propulsion comes from.
There's also a certain engine that's both efficient and gives you sufficient thrust. A Vasimir engine. These could get us to Mars in 3 months rather than 8 months to a year.
They work by turning matter into its fourth state. So they take a conventional gas and ionize it into a plasma. Once it's in a plasma form, it's easier to inject large amounts of energy in through various forms like radio frequency heating, which allows the temperature of the gas to be taken up to, say, 1,000,000 degrees, so hotter than the surface of the sun. And then you can eject it out of the back in a more efficient way, which gets you a higher level of miles per gallon, but also then gets you that higher thrust.
How soon do we think this might happen, if it does at all?
There's a saying in the space industry as well as the nuclear industry that it's always 50 years away. So 50 years ago, they thought it would be done today. And today we think it's about 30 to 50 years away as well.
Just a mere half-century then. Thanks to James Sadler from Airbus.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
You're listening to The Naked Scientist with me, Izzy Clark. So far in our attempt to leave the planet, we've looked at where we could go and how we would get there. But if we did leave, how can we prepare for that? In the next 50 years, maybe sooner, we might even be able to take holidays that are out of this world, quite literally. Commercial companies are selling tickets for a short ride in space for the cheap price of $200,000 per ticket. But if we all decided to jump on a spaceship and leave our lovely little blue dot, chances are we wouldn't do too well. It's a lot for our bodies to process. One company called Blue Abyss is hoping to change all that. I spoke to the company's director, Simon Evitts.
We've got something that's akin to the aviation industry in the very, very early days, where there was just a few planes. Right now, we've only got just a few commercial spacecraft, but it will grow exponentially in the decades ahead. If you think back to the gold rush days 150 years ago, you had lots and lots of people rushing to go and try and find those little gold nuggets. They needed the right equipment. They needed the right knowledge. How do you pan for gold? How do you work out where things are and what to do? We're going to be those individuals, that company that provides the spades, if you like, and the knowledge for the many thousands of people who are going to go into space in the future. And we need a way to prepare and train people to be able to go into space. And where at the moment can they do that? If they're not a government astronaut, nowhere. So that's what Blue Abyss will be. It'll be providing that capability.
Okay, so this is for, I'm not a NASA trained astronaut. This is, say, if you and I wanted to buy a ticket to go out into space, we could do so and then get ready for that at a centre like Blue Abyss.
Exactly that. There are elements of preparation for space that a regular person can get here and there, but there is nowhere that has everything all in one place to the standards that will be required for either a member of the general public like you and I, or even for professional astronauts in the future.
How does that even work? What sort of processes would we have to go through?
Somebody who's going to go into space will need to be familiar with and be able to be comfortable with high levels of G as you go into and return from space. They will need to be comfortable with weightlessness itself. They'll need to be knowledgeable with regards to emergencies that can happen and what they should do. They would need to know what's going to happen to their body when they go into space so that they're prepared and not surprised. And all of these things can be provided by a centre like Blue Abyss.
Well, I was going to ask, because how can you do this? Obviously, to practice, we can't send people up into space. So how do you get around that big old problem?
It's really taking the more important elements of a space flight and being able to replicate those as best we can on the ground, which we can do if we have the right apparatus. So a long-arm human centrifuge can enable us to spin up to high Gs. So when we're sitting in our chairs, right now, if we lift up our arm is at 1G. The weight of our arm is the normal weight that we experience. If that arm was suddenly 5 times its normal weight, you'd find it quite hard to lift up. That would be someone feeling 5G, except all of their body would be feeling 5 times heavier than normal. And that occurs when we're accelerating fast. So a centrifuge with somebody in it, if it's accelerating fast, will increase the centrifugal force, the Gs you feel. And that's what happens, of course, when we're in a space rocket or a space vehicle that's launching up into space. It's accelerating fast. So the G profile, if you like, the length and type of G that is experienced in a launch to space can be replicated in a long-arm human centrifuge so that that person then is comfortable and understands the feeling and is able to cope with those feelings when the real event happens. But also weightlessness through a parabolic flight service and the ability to be able to be trained and to get a feeling for being in space through a neutral buoyancy pool.
What is the importance of this parabolic flight? How would we see that if we were to go into space?
Well, parabolic flight provides short parabolas, like going over a humpback bridge, where at the top of that hump, if you like, you get 20 to 30 seconds worth of weightlessness. That's like a mini version of what will be the suborbital flights that are coming, where someone will experience 3, 4, 5 minutes of weightlessness. And although a parabolic parabola only gives you a few seconds, you can still use that to prepare for certain elements that you'll need to know about and be comfortable with in these forthcoming flights, like, for instance, how to get back into your seat and buckle yourself up safely.
And aside to some of these actual physical trainings that really put us through our paces, what else would other trainings provide that we need to be aware of that you don't necessarily think of when taking on a mission like going into space?
Well, there needs to be a number of briefings so that the effects of being in space on the human body are understood, because there are effects for most of our physiological systems when we spend time in space. So, for example, the first few days in space, most people tend to have space motion sickness. And so we really need to understand that, understand how to deal with that to try and minimize it.
With the training program that you'd offer, how long would that take?
We're going to offer short and long packages. So some of the short packages would be individual elements. It could be a high G half day, it could be a parabolic half day. And then the fuller courses, training courses, would be probably in distinct 1 week portions. And how much is done will depend on what that individual is going to do. Are they going to do a suborbital flight? Are they going to go into orbit? And so there'll be different length courses with different elements according to what is needed.
Whilst Blue Abyss won't open for a few more years, having spoken to Simon, I felt really excited and a little bit queasy at the prospect of taking a holiday in space. What would that trip feel like?
Hi, I'm Dr. Alex Stevenson at Kinetic in Farnborough.
Please explain where we are, because I am very excited.
So we're at the human centrifuge facility in Farnborough. So at the moment it's the only human-rated centrifuge we have. So it's a great big spinning arm. It's about 30 foot in radius, so 60 foot in diameter. And it's been here since 1955. Primarily in the early days was to research the effects of these G-forces on humans. More recently, actually, to train our fast jet pilots how to cope with the forces they experience when they're manoeuvring their aircraft. And we also do a bit of space research. And we've, in fact, done some training of sort of space tourists up to the International Space Station, and now recently doing some research looking at the respiratory effects of high G-forces.
So basically, to put it very bluntly, it's a little pod on a massive metal arm that gets spun around very, very quickly.
That in essence is what it is, yeah.
Now I can just see our first victim has climbed into the centrifuge. So tell me what actually happens once this giant arm starts to spin.
So the actual arm takes a bit to start going, so it'll idle around the room a bit, and then the motor will kick in. And how we've set it for at the moment, it will accelerate at 1 G per second. So if we go to 3G, it will take 2 seconds to get up there. So very quick. And then it sort of sustains that G level for however long you want, really. For today, I think we'll just keep it to 15 seconds. Now, what the person in the pod feels is that there's a sudden increase in their weight. So moving their hands and arms around is much more difficult. And also because the weight of their blood has increased, it will tend to head downwards. And what they might experience, depending on how low the blood pressure drops, is a loss of vision. And that's caused because the eye has actually got an internal pressure to hold it in that spherical shape, and it's harder for blood to get back into that eye. So you lose your vision first, and once you've lost your vision, that's when you end up not getting enough blood to the brain, and then you end up losing consciousness. But hopefully we won't get that today. We'll just see a bit of visual loss, which it's very dramatic and easy to see.
So does this mean I can have a go?
You can indeed have a go.
Oh my goodness. I better go and suit up.
Oh, we shall take you through.
How excited. I'm really excited.
Okay, so I didn't actually have to wear a spacesuit, which was rather disappointing. I climbed into the small pod, ready for a spin.
Israel, hi, can you hear us?
Yeah.
Lovely. Hello, control. And if you'd like to set us up for a 2.4 G run, and we'll take that as our first taster for 15 seconds. And then if you're happy at 2.4, we'll take you up a few little steps beyond that.
Perfect.
2.4 G, 15 seconds. Stand by.
Here we go.
Initially, I'm sat upright, but as the pod accelerates around the circular room, I'm tilted sideways, the top of my head pointing towards the centre, and this causes the blood to rush down towards my feet, much like a pilot would experience in flight.
And you can talk to us?
Yeah, it's okay. I was expecting it to be quite intense, but it's actually just like a massive roller coaster ride.
Well done.
In fact, by my 5th run, we took it to a maximum for a newbie like me at 4.2 G. And yep, my vision disappeared.
Yeah, vision started to go, but yeah, it's just cleared completely.
By tensing legs and stomach muscles, you force the blood back up towards your head, and suddenly your vision clears. Hopefully. Whilst I recovered from the motion sickness, Alec explained why it's important to run these practices.
So there's a medical thing, so we need to check that the actual forces that we're subjecting our pilots and astronauts don't cause them any physical harm. There's a familiarisation piece as well, really, because it's an unusual sensation that they wouldn't normally expect to have in life, particularly for astronauts. Those sort of accelerations are just really for space. Although there's not necessarily for that kind of acceleration, that chest-to-back acceleration, training per se we can do, it's a sensation that they need to be familiarised with so that they can get on with what they should be doing, concentrating the tasks they may have to do in the spacecraft. As you were about 4G, so we should be able to get you up to 9G with the kit that we've got and some training.
I don't think I'm quite ready for that just yet. So the sensation in your body is so strange. Like, everything feels a lot heavier. As astronauts take off, their lung is almost feels so heavy. Does that have any health implications? Like, how can we even study that?
It does have health implications. It does affect how your lung works. And obviously, our lung is very important. It's how we get oxygen into our blood. So one of the things we can measure how that acceleration affects the amount of oxygen you get in the blood. And we've probably all seen a lot of clinical programs where we've seen a little clip that you get on your finger, which is called a pulse oximeter, which measures that percentage of oxygen that's the hemoglobin saturated with. And we can do that, and we can see that that is markedly reduced when we're under that sort of acceleration. The good news is when we turn the acceleration off, that tends to return to normal. As the lung is quite spongy, it distorts under its increased weight. What you end up doing is stretching the top parts of the lung, so the parts where actually at your chest, and the bottom parts of the lung, which are near your back, get compressed. And that there is an element of that when we're just lying on our back, but because it's only 1G, there's only a slight difference between the top and the back. And as we increase the levels of G, we just amplify that difference. So we're concerned, I suppose, under GX that we get a part of the lung at the base that's got under so much pressure that it closes off and doesn't communicate with the atmosphere. And because it can't get air into and out of the lung, the blood that flows through it just doesn't pick up any oxygen. It contributes to what we call a pulmonary shunt. It's a proportion of the blood that we're pumping out of our heart that doesn't actually pick up oxygen when it runs through the lung. And obviously that mixes with bits that do pick up oxygen and just lowers out the average saturation we've got. Now, the issue with the top part of the lung is that it gradually gets stretched, and like any mechanical component, will eventually cause damage if you stretch it too much. A lot of the stuff that we're doing suggests that the levels we're doing are safe, but there is a degree of stretch in there. We need to be careful that if we've got some individuals who already have issues with their lung, that if we stretch any further, are we actually then going to cause an issue, a tear or something like that? So it is something we need to consider.
That was Alex Stevenson from Kinetic, and you're listening to The Naked Scientist with me, Izzy Clark. We've just heard my small attempt of astronaut training, and I don't think I'll give up the day job, but that was just a taster of a space launch. Turns out there's a lot of other health impacts, more than just motion sickness, that those travelling into and perhaps even living in space will have to battle with.
So we'll start with the cardiovascular side of things.
That's Julia Attius. She researches space physiology at King's College London.
Here on Earth, when we stand up, we have blood that collects generally in our lower limbs because gravity pushes it down. So our heart has to work quite hard to get the blood back up towards the head to make sure that we don't pass out. Now, when you're in space, you generally have more blood in the chest area than what you would have on Earth. So because it's already located higher up, the heart doesn't have to work as hard to get it up to the brain. So the heart loses a little bit of its strength and its muscle mass because of that exact reason. Now, when you come back to Earth, the problem is that those astronauts are now re-subjected to gravity again. So the heart does have to work hard to get blood from the limbs back up to the head. But they've now got a slightly weaker heart because it hasn't had to do as much. That typically can result in something called orthostatic intolerance, which is the inability to remain in the standing posture because those cardiovascular regulation mechanisms have had a little bit of a rest and they've become a little bit weaker and inefficient in their job.
What about the rest of our body? What's going on there?
One of the other major issues is to the musculoskeletal system, so muscles and bones, and it's very similar as to what happens in both. Astronauts tend to lose muscle mass, so the size of their muscles, and also the function, so the strength of those muscles as well. The two tend to go hand in hand. And we also lose some of our bone mineral density. And that's mainly related to the same reason. So again, if we think about Earth, every single day, multiple times a day, we're standing up and we're moving around. And what that does is enable our feet and our body to come into contact with the ground. Now that impact, that loading, is what's required to normally maintain muscle and bone strength. Because astronauts don't have that, they don't have anything that they're coming into contact with, they're essentially floating. So because they lose that impact, the muscles and the bones, particularly in the lower limbs, gets much smaller.
So essentially, your muscles and your bones waste away, really?
Yes, in the lower limbs they do.
Gosh, that doesn't sound very nice.
There's good news.
And what's that?
This was recognised very early on. So the good thing is that there are plentiful countermeasures in place that help to prevent these things from happening. So at the moment, astronauts stay on the International Space Station typically for about 6 months. They have a very robust exercise routine. It's comprised of about 2 to 2.5 hours every day, which really helps to maintain much of that muscle and bone mass and helps with the cardiovascular side of things as well. And there are also some dietary stipulations that help to keep muscle and bone healthy, like calcium supplements.
And obviously out in space, we've got the sun blaring down. I mean, it's bad enough here on Earth. We always put on sun cream. So what's the risk of radiation?
Yeah, so the risk of radiation going to Mars is probably the biggest issue of all of them at the moment. It's probably the main limiting factor. Aside from the engineering feat and the craft that's going to get them there and back, radiation is probably the most vital risk. So at the moment on the International Space Station, astronauts are still protected from the Earth's magnetic field. So they do have increased radiation exposure, but it's nowhere near as much as astronauts will have when they do venture to Mars.
What sort of damage can radiation cause?
Radiation typically takes form of high-speed particles, if you like. Those particles can actually tear through DNA molecules. It can damage the information that they have given for cell production. And the main issue, which we can all relate to, is the cancer risk.
And so we've looked at all the physical things, but what about what's going on in their heads? Is there a psychological impact from going into space?
The psychological aspect is really interesting and packed full of a number of factors. Their sleep is definitely an issue because at the moment on the space station, astronauts have a day and night cycle every 90 minutes or so. So that's really quite difficult because you don't get a patch of darkness. So their circadian rhythms, which are the rhythms that help to regulate day and night, are absent. So that can really take a toll on their psychological well-being. But also the confinement. They're essentially stuck in a tin can for 6 months with people whom, of course, they know, but it's not like you can run away to your bedroom if you want to have some you time.
Yeah, but like major cabin fever, really.
Exactly.
What do we know about long-term space flight? How long do people actually spend up in space, and have they looked into anything that is longer than... Because we're talking if we want to colonise somewhere that's like maybe spend a lifetime or 20 years in space. Do we know anything about that?
We've learned a lot about the impact of spaceflight on the human body for a number of decades now, which has really been valuable. But we're really entering into another arena, and there is still definitely a lot of research that would need to be done to help pave the way and to understand what it is exactly that we would be expecting and how best to counteract that.
Our body certainly takes a hit in space then. That was Julia Attias from King's College London. And those are just some of the changes that we'd need to adapt to if we lived in space. What about the air we breathe or our food? Here on Earth, we rely quite heavily on our plant biodiversity for a lot of that. But could we take it with us? I went for a stroll around Clare College Gardens in Cambridge with plant ecologist Howard Griffiths.
So, welcome to Clare Gardens.
I don't think I've ever seen such a beautiful garden in my life.
So, Howard, what have plants ever done for us?
How can you ask such a question? Plants are the basis of life on Earth. They are the Earth's life support system. Everything we do is derived from plants. either in terms of fossil fuels, which represent plants that were buried underground in millions of years ago, or in terms of the basis of all the foodstuffs that we consume, or in terms often of many of the clothes that we wear. They learnt millions of years ago how to harvest the energy of sunlight and use that to take up an abundant resource within the atmosphere, carbon dioxide, and turn it into organic carbon. And they contain an enzyme which is the only enzyme that has evolved in a large enough scale to be able to do that, to support what we now know as life on Earth, in both the oceans and on land.
Yes, so quite a vital role then. So if we were to go, say, to another planet like Mars, could we bring them with us and try and work it out?
Absolutely. I mean, many experiments are being done in various space flights in order to test out how plants grow under extremely low gravity, whether they can grow, because of course they're going to be slightly disorientated because plants can sense gravity and normally send their roots down and their shoots up. And without that, we would need to devise special chambers perhaps to help them simulate which way is up and which way is down.
I'm imagining sort of giant pods that you just sort of come across that look like a beautiful oasis or something like that.
Well, that's a fairly large scale. I suspect the prototypes I've seen have been slightly smaller, more like small chambers, but nonetheless they are thinking about whether we might be able to grow plants. So we would need plenty of water, we would need carbon dioxide in appropriate concentrations, together with the additional nutrients that they would need to be able to take up from the soil and grow.
Now, is this what we categorise as biospheres? Are they the same thing?
Very similar. One might imagine that a space station as a permanent habitation might look something like a large experiment that was conducted in the Arizona deserts and is still going on. It's called Biosphere 2, that had some problems, let's say, and there may be lessons from that biosphere that might help us inform what would be needed on another planet.
So what were they looking to find with these biospheres?
Well, in Biosphere 2, they first of all set out to try and create a completely self-sustaining environment with oceans and deserts and different habitats, into which a number of people were going to try and live for a whole year without any external intervention.
Was this included like an oxygen supply? How did that work?
Well, the idea was that the plants that they would grow would help to sustain the oxygen supply and provide them also with food to eat.
Well, it sounds amazing. Did it actually work? You alluded to some technical problems.
Well, quite apart from the interpersonal problems that are said to have happened, the individuals lost a huge amount of weight because they simply couldn't grow enough food to support them. And there were also terrible problems in terms of maintaining the right balance between carbon dioxide and oxygen inside those biospheres. Partly because of the materials they used both in the soil, which had too much organic material, and so basically the microbes in the soil were just busy consuming oxygen and converting that to carbon dioxide. So the soils were respiring too much. And the other problem was that the concrete that they built the buildings from was also absorbing carbon dioxide and oxygen. So in the end they had to introduce pulses of oxygen to try and sustain the environment.
So even then, if we were going to try and replicate that, we'd even need to get the practice run here on Earth right first.
Well, the idea that plants will give us the oxygen that we can breathe is one of those sort of long-standing fallacies. Yes, plants did give us the oxygen we breathe over the last 3 billion years, or 2 billion years. Currently, they're in balance. So plants and organic material respires as much, consuming oxygen, as it produces every year. So trying to create an environment where plants can produce the oxygen we need to breathe means that we need to take away that carbon and store it somewhere, as our fossil fuels did 300 million years ago.
That's quite a long wait to get to that.
Exactly. It would be a real problem. So you would still have to find a way to manipulate the oxygen concentration independently to keep it at a high enough level. It would take you a very long time to build a self-sustaining environment such as we have on Earth.
Okay, so perhaps we're not quite there yet. So what would some of the other challenges be of growing plants on another planet or in space?
I think overall, creating the correct atmosphere for them, finding enough water, getting enough soil, which didn't in itself alter the composition of gases that we were trying to grow these plants in or live in ourselves alongside them. And overcoming other issues like differences in gravitational pull relative to what we have on Earth.
So our plant situation is looking unreliable. The technology still needs to be developed for a rocket that can get us there and bring us back, if that's even an option. And we still need to carry out further tests on Mars. So even if we could colonise a planet, should we? I'll leave Adrian with the last word.
One answer to the question is, sure, why not? That sounds really fun. But there's another way of thinking about that question, which is something like, well, why are we leaving the planet? If we have a system of society that's extremely unsustainable and tends to, break planets, for instance, one that pollutes a lot, one that tends to over-extract resources, that kind of society, moving to another planet isn't really going to solve anything. It's simply we're going to bring the same mistakes with us. The idea that this heroic moonshot effort to colonize other planets is somehow a solution to a lot of the problems that we have is got the same problem as all technological solutions. The problems that we have, if you don't solve the social practices, if you don't solve the ways of life that we have that are unsustainable, a technological fix is just going to be a band-aid.
That was Adrian Curry from the Centre of the Study of Existential Risk at Cambridge University. And thank you to all of our other guests this week. That's Nikki Medusuthan, Anne-Marie Trio, Andrew Coates, James Sadler, Simon Evitts, Alex Stevenson, Julia Attias and Howard Griffiths. Join us next time when we'll be kicking off with the science of football, the physics of bending it like Beckham, plus the psychology of being a football supporter. The Naked Scientists comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. I'm Izzy Clark and thank you for listening. Goodbye.